Now let's get started with the first example that we're going to build using LangChain. In this example, I'm going to show you how to process a JSON document containing different child JSON documents representing a movie dataset. And then once they're loaded into Redis, we're going to enable a search, or more specifically, a similarity search using the Redis query engine. All of this implemented using the LangChain framework, right? So this project that we're going to use can be found here on the description of this video, right? So you are going to use that project and make it available on your machine. Once you have it open, you're going to notice that inside that project, you're going to find three Jupyter notebooks, right? And those are going to be the examples that we're going to build throughout the series. For this particular example, you are going to use this one called Vector Store, right? So in this example, like I mentioned before, we're going to load a movie dataset. This file is on the project as well. So under this data folder, you can see this file called movies.json. And then this file actually has this JSON document, which has this array called movies. And within this array, you're going to find 10 movies about Marvel anti-heroes. For those of you that know me or follow me on social media or know me personally, you know that I'm a huge fan of Marvel characters. So all those movies here represent a character from Marvel that is a anti-hero. So for example, Blade, the Punisher, Daredevil, Ghost Rider, Elektra, etc., etc. So there are 10 of them right here. So what we're going to do is load all of this into Redis, and the source material for our search, or for the similarity search, is going to be the plot of the movie, right? So based on the plot of the movie, we're going to be able to find a specific movie given a human description from the top of our head, right? So this is the basis of what we're going to build, right? I went ahead and already executed a couple of boilerplate code that it doesn't necessarily have to waste time with this. All the installation of the requirements and the dependencies that we have, in this case, LangChain Redis. I already also import all the libraries that we're going to use, the import clause of our Python code, and then we can jump straight to the setting up the Redis connector. Now, to set up a Redis connection with the with LangChain and the Redis API, you are going to use this packet Redis, and then from URL, you are going to provide a Redis URL, a valid Redis URL, right? So in this case, we're not going to use Redis database running locally, so we can completely change this. We're going to use that database that we've created before, right? So what I am going to do, I'm going to access my Redis Cloud account, and then I'm going to pick up the database we created before, and then I'm going to click here on the connect button, right? So I'm going to actually put myself here on the left so you can see what I'm doing. Instead of Redis inside, this time we're going to scroll down and pick up this option Redis CLI, right? So what we're going to copy here is the Redis URL, this specifically here, right? Not the entire command, because this is for you to connect with Redis CLI. So what we are interested is in the URL. So before copying, make sure to click on this I button so it can show up the password for your database. Otherwise, the connection is going to fail. And then you're going to copy this, right? So this is the source of our copy, right? So I'm going to go back to my PyCharm and then replace this Redis URL with this one, which represents the database that we have on Redis Cloud. If we execute this, we're going to be able to see this true statement here. This represents this ping request that we've created on top of the Redis client, meaning that we're able to reach the database on Redis Cloud, which is good, right? That's what we want. And then the next step is going to be preparing the sample data, right? So in this case, what we're going to do, we're going to process this file movies.json, right? So we're going to use the Open API and then provide the file name. And then we're going to load all this file into this variable called data, right? And then we're going to do a for loop into this data, specifically on this element called movies, because we want to read this JSON element. And what is this JSON element? Is an array, right? So that's why we are going to iterate for each one of those, the elements of this array, we're going to have this movie component. And then from this movie component, we are going to create the first basic construct of LangChain, which is the concept of a document. For those of you that are already familiar with LangChain, you know that documents are the base, the raw material for you to create and instantiate embeddings, right? So you have to create a document for it. And for each document, we have to set what is going to be the page content, which, in other words, the actual essence of that document. So what we want is to, from the movie, to read the plot of the movie. So the plot of the movie is confined within this info attribute, and within the info, we have the plot, right? So that's why we are using this JSON construct to navigate over the JSON structure. And also we are going to provide, this is totally an optional step, but for this particular use case, it's going to be useful. We're going to provide a metadata, right? So the metadata is going to be important later on because we're going to use those fields specifically here to further optimize the results of a query, right? So similarity search is going to be the best effort to find whatever search that you're gonna try to do, but then you can use optional fields that you're going to specify here on the metadata to further filtering and try to find the exact movie that you were looking for. So in this case, we're going to use the fields title of the JSON document, the year, and the rating, which is also within the info component. So let me execute this, and then at this point, we have all the documents already loaded in memory, so we can actually double check this. If we try to find the first element of this array, documents, is going to show us this document equivalent to the Blade movie, right? Let's see if this is actually true. Yep, so the first element of the array is the movie Blade, right? So we're on the right track for the code. So the next step, we have to create the embeddings, right? So the embeddings themselves are not to be created at this step, right? So what we are doing here, using this Hugging Face embeddings, we're basically instantiating the source of the engine that is going to be used to create the embeddings, right? So we're going to store on this variable here that we call embeddings, right? So right now it's created. We're using this popular model name, MS Markov, just Dilbert Basic v4, right? Actually, it's up to you. If you want to change this code and maybe use another source of embedding engine, so perhaps OpenAI, the engine to create embeddings, you can definitely use it here, as long as you instantiate an instance of a valid embeddings engine from the LangChain SDK. And this is where the magic is going to happen, right? Before I explain this part of the code, I would like to highlight the fact that if we look to Redis Insight right now, so this is the database that we've created on Redis Cloud. There are no keys stored on Redis Insight, meaning to say that the database is empty, right? So once I execute this code, what's going to happen is that all these documents and the equivalent embeddings are going to be not only created but stored on Redis, right? So let's execute in a minute, but let me explain what this code actually does, right? So the most important element here that we're creating is the Redis vector store. So this is the implementation of a vector store from the LangChain standpoint. So this is a specialization class that implements the right behavior that is expected for the LangChain perspective, right? And then we're calling from this from documents function call. So what this function provides you with is the ability of in a once, right, to perform three operations, right? The first one is to store the documents on Redis. The second one is to, out of those documents, create the respective embeddings, right? And then also store on Redis. And there will be a third thing being also that's going to be happen here, which is the creation of an index, right? So what is the index, right? So this is something that is peculiar to Redis. So the Redis itself is a NoSQL database, right? That's basically provides different data structures for you to work with. But when it comes to search, whether if it's a vector or JSON search, there's something called Redis Query Engine that in order for perform the queries that you are expected to happen, you need to create a construct called index, right? So this is going to be like think about as if it was a metadata for your vector, right? So in this case, we're going to create an index called movies, right? And then this index is going to have the following fields that are going to be searchable, right? So the field title, year, and rating. Title is going to be a text. Year rating is going to be numeric fields, right? So let's execute this code, and then you can see what happens. If we go back, just execute it. If we go back to Redis inside, you are going to see, if we hit enter again, you are going to see 10 keys. This is here, 10 keys stored on Redis. Each one of those keys are basically associated with a JSON payload that you can actually uh, when you click one of those keys, you can see the side panel here with the content of that key. And then you can see that here you go. Like, for example, the Punisher movie, the text is the equivalent of the plot that we've read, and then the year and the rating, right? But most importantly, you're also going to see a specific field here called embedding that is going to contain the array of float values that represent your embedding itself. So all of this, right, will happen when you execute this single line of code called from documents, right? So I would like to highlight the fact something really, really important here. This type of construct, right, it's very handy for you for education and demonstration purposes. That's why we are using it here right now. But you have to keep in mind that this can be extremely time consuming in terms of resources, because we're dealing here with a limited data set. 10 documents it's going to be executed relatively fast, right? But let's say that you were not dealing with 10, but maybe 10,000, right? So what would happen if you use the same construct with 10,000 documents? For each one of those documents, it first would need to create an embedding, right, which is already time consuming. And then you would create the write operation into Redis for that document. For each one of these 10,000, it would take a while to execute, obviously, right? Because in computer science, there's no magic, right? So this is a type of operation that instead you would better off maybe instantiating first the vector store and then creating some sort of a more optimized way to load all the documents, perhaps using some parallelization, concurrency, or in batches, something that is not necessarily going to load all of them at once in a sequential manner, right? So keep that in mind when you are dealing with this type of construct and you are loading a considerable data set. Now that we have all the documents already and the embeddings stored on Redis, right, let's start executing a first similarity search example, right? So in this case, I'm going to tell you up front what I'm trying to look at for here. I'm trying to look for the Punisher movie, right? So I know, because I'm a huge fan of the character, I know that basically the storyline of the Punisher is that he seeks revenge for his family's death, right? So, but if you look to this query here, and if you compare, here's the Punisher. This is not what is written in the plot of the movie. This is what I remember from the top of my head about what the Punisher storyline is about. So this is a very good example of the use case of similarity search. So users are going to use their own words to perform search, and somehow, magically, the search engine need to be able to find the proper result. So that's where the technology of vectors come into play, right? So in order for this to be implemented, you have to create called the vector store that we created before. You're going to execute this function called similarity search, right? And you're going to provide your query, right? That's the first parameter. And then you're going to provide also the K parameter. So what is the K parameter? This is, think about the K parameter as the tolerance of how loose or precise your search is going to be. Like, the smaller the value that you provide to the parameter K, the less is going to be your tolerance for random results that doesn't necessarily are close enough to what we are looking for, right? So in this case, number 2 represents a very leaning towards precise results. So let's see how this goes. So after we get the results, we're going to walk over those results and print the documents. So let's see what we find here. And then, as you can see here, we were able to retrieve 2 documents, right? The first one represents exactly what I was looking for, which is the Punisher movie, as you can see here. Again, even though the query that I've used it here doesn't necessarily isn't a direct equivalency of what is written on the plot, right? So this is the beauty of the vector technology, right? It uses the proximity of vectors to try to find something that is roughly what users are trying to find. However, as you can see here, it also managed to find another movie from Ghost Rider, actually. And this movie, I would guess that it only came up here because I've used the word revenge, and then somehow maybe is kind of a try to mimic with the equivalent of the words, I don't know, vigilante. I'm all in wonder here. I don't know. And also, the Punisher movie also uses the word vigilante. So vigilante is usually in a plot of a movie they're seeking revenge. So I don't know. Maybe that's the rationale behind the embeddings proximity that was found. But what is important here is that, yes, I was able to find the first entry as the most closer thing that I was trying to look for. I could be happy with this, but let's say that as a user, I would like to fine tune and find exactly what I was looking for. And perhaps I know roughly the plot of the movie, which is, yeah, he seeks revenge for his family's death. And I know this movie is from 2004. So what I could do is to use the feature called similarity search with metadata filtering, which comes back to what I was saying before about the need for you to perhaps enrich your data and your data set with metadata specifically, right? So since we have metadata associated for the fields, title, the year, and the rating, I can use the field year, for example, as a filter condition. So in this case, I created this filter condition here called the year is 2004. So as you can see here, the Punisher movie is 2004 and Ghost Rider is 2007. So now I am doing again the similarity search, providing the same query, the same k parameter, but with a filter condition, right? So let's execute this code right now. And then as you can see here, voila, only the Punisher movie actually shows up, right? So a couple of things deserves our attention here. The first one is that, yes, you can further optimize your queries with filtering using metadata that you have specified beforehand in order for this to happen. So that's point number one. Point number two is that even the previous query already provides us a very decent results of a search, because think about this, out of the 10 movies that has different plots, it was able to filter only the ones that has to do with elements like revenge, his family's death. So I know the Ghost Rider storyline as well. So, and I know that the Ghost Rider is a character who does what he does because he seeks revenge for the death of his father, which is his family. So it kind of for my perspective, that search was spot on, right? Because it found movies that indeed has to do with the seeks of revenge. But anyway, it filtered out all the other 8, which has nothing to do with this. So that means that the concept of vectorial search using vectors proximity was very well applied, right? Another feature that is actually from LangChain by itself, right, is something that you can use for debugging or troubleshooting purposes. Sometimes is the usage of scores, right? So you can provide your similarity search and retrieve the scores associated with this. So I'm going to execute here and show you to see how this works. So as you can see here, I basically repeat the same search with the same query, k parameter, and the filter condition. Not surprisingly, it found the same movie that I was trying to look for before. But along with the document retrieved, it also came with the score. So what is the score? This is a mathematical calculation about the proximity of the vector that closest approximate to what I was looking for, right? So this, you can use that score to sometimes compare one if it's higher or lower than the others to see if your criteria of filtering, perhaps the fine-tuning that may be required in an index level on Redis needs to be further optimized, or perhaps the data type of the metadata. And then you can use this to see how close your searches are actually being, right? So this is sometimes is useful, right? Before we wrap up, I would like to show you something more, which is you have the ability with the LangChain framework to actually delete data, right? So in this case, as I mentioned before, you have 10 documents stored on Redis. And let's say, for the sake of the argument, that I would like to delete not only those documents here, but also the index, the movies index that was created on that operation before. So you can do all of this with this by calling the vector store one more time, and then you're going to access this option index. You can call the function delete, right? Passing this parameter drop to true or false, right? So if you set this parameter drop to false, what's going to happen is you're only going to delete the index itself, but the data is going to still be living on Redis, right? So that's an option. Or if you set to true, that's what I'm going to do right now. I'm going to execute the code, and then if we refresh, no more data stored on Redis. And if you look here for the indexes, there are no more indexes created, so which is good. So what you can do with these options is actually get rid of some data that is no longer being used, right? Another option that you can do the same thing instead of doing this programmatically, right, is using time to live or TTL. You can, as you set documents, you can set time to live values for those documents, and then they are going to be automatically expired using the Redis engine for TTL. So, which is kind of a handy for situations where you know roughly for how long those values are going to be needed or useful, and then you don't want to have to explicitly create code to get rid of that data. So maybe using the time to live approach could be something that you can leverage. But regardless, you have ways, as you can see in this example here, you have ways to not only create documents, store them on Redis, and make them available for search purposes, vectorial search purposes, which builds the approach for you to implement similarity search. So I hope you find this content useful, and then in our next example for the next video, we're going to actually see how to create the constructs and LangChain to use Redis as a cache, because this is one of the most famous use cases for Redis itself. But instead of only using it as a cache, we're also going to cover the fact that we're going to use it as a semantic cache. But I'm going to spoil the beauty of the next video, and I'm looking forward to see you in the next one so you can know how to do this, all of this with LangChain.